All right, guys, let's take a look at section 2 and thermostat and temperature controls in the module on 03314 control circuit and motor troubleshooting. So this one, this particular video will just focus on that second section related to the temperature, thermostats, and temp control. So let's talk about some of the things that we need to do with this. So first of all, some of the objectives in this chapter is to really describe the operation and installation of various types of thermostats and temp controls, and we'll look at its operation, maybe how to identify or troubleshoot certain thermistors. We'll take a look at how to install and wire thermostats, and maybe how to troubleshoot some of the functions on a thermostat. All right, and your performance task will be to simply wire and check the operation to make sure it's right, and then adjust the cycle rate on a thermostat. So we'll talk about some of those things. So obviously a room thermostat is designed to control the temperature of the air within a room. Typically you're locating them on the wall, outside of the line of sight of any type of heat source, away from a heat source. That means you don't put them over things like microwaves and refrigerators, or put them next to copiers, things like that. All those things that in an office building you oftentimes see those activities happen, which can create some issues. Typically, any type of a thermostat would have some sort of a set point, as well as obviously maybe some indication to say this is what things are, this is what it is. So that's primarily what goes on with it. Now, specifically, there are different types of thermostats. You can have more mechanical type thermostats. You can have thermostats that are electronic. You can have the mechanical thermostats usually would be some sort of a bimetal that might incorporate some sort of a metal that might entail like copper or brass is one of the metals, and then possibly Invar is another type of a metal, which is about 35-36% nickel, and those are, and what they are when they fuse these two metals together. So as you can tell by looking at these two metals fused together, they actually expand and contract at different rates. So you end up seeing it as a twisting motion, which is incredible how when they make a thermostat, how they can it's predictable that they do this. So it's pretty interesting how they set that up. Some of the things that are, I think, when I think about functions of a thermostat and what do I want it to do, I think a thermostat actually is pretty amazing how a very inexpensive little part that can control, if it's mechanical, you can control within 2 degrees of set point in most cases, and electronic maybe within a degree. It's pretty amazing that you can do that. They will, on the mechanical side, where you might be dealing with the bimetal type sensors as opposed to thermistors, there are 2 different types that you might see. So one of the types might be like that bimetal bar like you're seeing on the left side of the image, whereas the probably more common would be the spiral wound. So when you think about the old round Honeywell T87 thermostat that was used for many, many years and still in use in some applications, they have an actual wire wound or a spiral wound bimetal. And that bimetal just kind of moves and shifts predictably based on temp. All of these thermostats all of those particular thermostats, I would say, they have some things that they need to do. Like one of them is they have to switch contacts. They're going to do some sort of contact switching. So for example, I need this set of contacts to create a nice, quick, snap-acting contact closure to allow a heating system or a cooling system to function as you want it to. And of course, when you open it, you want it to open fairly quick or fairly fast. And the whole reason behind that is you'd like it to prevent any type of arcing that would be going on inside of that, because any level of arcing that would occur within those thermostats are going to eventually create some resistance, which can start to cause problems for us. So an older thermostat would be much more likely to see that issue. So what we oftentimes will see is we'll have something that might be a snap-acting thermostat. So on some of the thermostats that I've seen with the bimetals, they would, all of a sudden they'll get to a point and then they'll snap right into position. So there's very little arcing that occurs in any of those. So it's pretty amazing. And obviously the other things that are interesting about these is, so many of these thermostats are, they have to handle some of even the toxicity and some of those types of things that go on within a system. It's pretty amazing that they have. Now, we also have thermostats that are, I would say there's still a few thermostats out there that have to work on what we call self-generating systems. And the self-generating systems are usually systems that operate on like a 3/4 of a volt DC. So your book on page 15 in that section, they talk a little bit about the self-generating systems. They'll generate about 750 millivolts from a pilot flame, and this is typically what we call power pile type systems. And of course you can buy with just simple switches, but there are specific thermostats that are designed for that. So additionally, to talk a little bit about some of the thermostats and some of the interesting parts of this chapter is some of the thermostats for many years they use Mercury. And of course, Mercury thermostats, in most cases, the older ones, they were, if you were replacing a furnace, you'd pull the old Mercury one off and you'd, give it to the wholesaler, or you'd recycle it. And of course, you can't just throw it in the garbage. It has to be properly recycled. Mercury is very hazardous. So primarily, we don't really see Mercury used for these applications, as of today. The only ones that are in there would be the ones that are left with, the customer doesn't want a different thermostat. They want to keep it. You can't take it away from them necessarily, but that's primarily what would end up having on there. So, and I'd mention also like about these millivolt thermostats, like the 750 self-generating thermostats. So one of the interesting things about those is in many of the fireplaces that you might see used in the industry, they would have a self-generating thermostat that would do this. So they would control the gas valve primarily. They didn't really pull in relays or anything like that. They didn't operate the fan. That was another circuit. But the thermostat itself would handle that. Or they could have used an electronic one. Nowadays, the electronic ones, if they're battery powered, can operate those power pile systems just very, very good. And so primarily nowadays, you really expect to see most thermostats going away from the electromechanical and closer towards what I would say is your typical operation with an electronic type thermostat. So let's talk about the operation of a thermostat. So there are two. There's a couple of symbols that are in here, and the first one I want to hit up on is on the circle to the left. That's kind of an on-off position or an on-off. So you might have an application where there's a switch on a thermostat that is either on, maybe it's heating or it's cooling or whatever it might be. You might have an on-off switch. But there's also switches, and that's not what this one's for, but there are also other switches that would allow the fan to operate in addition to maybe that would be completely separate. So you might have a fan on auto switch or a heat cool off switch possibly, or even a heat off switch. So there's a number of different ways. The second part of that is, I want you to see is the way they've drawn the symbol, I think is important. This particular symbol is going to open on a rise. So if you look at this, this is designed to look like the bimetal. And this is going to, a heating thermostat will open on a rise, is the way that that's going to work. Now, as it opens on a rise, that means that, let's say if you have a set point of 70 and the system is measuring 67 degrees, it's going to heat, and then obviously when it hits that 70, you would expect it to open up, or the 72, depending on the differential that we have in there. So that's kind of the operation of what you'd expect in there. Now, there are thermostats that actually do have a device that's called an anticipator. And the anticipator is a device that allows some of the current to, let's call it, go through a little heater. And it's designed to allow that system to take kind of the, let's call it the path of least resistance, to allow the circuit to basically, what you're doing is you're adjusting the amount of heater that is being allowed to use, or that's being used, to actually provide an anticipatory heat to allow the let's call it the bimetal to function, or so it will anticipate that I've reached my set point, so that rather than to prevent overshooting of a thermostat, that's really what its function is. So they want to try to prevent it from running an excessively long time period, so you're not overshooting the set point, and then you wait for it to cool down below the set point to the differential, and then all of a sudden it kicks back in, and then you have to wait for it to go beyond the set point. They're trying to minimize that, and that's the job of the anticipator. So in the electronic thermostats, we're going to be looking at some other ways that they will do this. So most of your electronic thermostats would have some sort of like a cycle rate adjustment. So the old thermostats, the way we adjusted the anticipator is that if you wanted the unit to run longer, you would actually adjust the heat anticipator to a larger number compared to the amperage that would go through there. So the more amperage in a circuit, you're going to create more heat. So by you adjusting that anticipator, you're actually adjusting it to provide a certain amount of heat to allow the thermostat to function. It's pretty interesting. So it does have some impact on differential. The anticipator also can be burned out. So in other words, if you run an excessive amount of current through a thermostat, this little resistor, this little, let's call it a variable anticipator, that little device can actually burn up. And so for example, if you're wiring up a thermostat and you accidentally touch the heating wire to the chassis of the unit, I mean, it will immediately smoke that anticipator. So they really can't handle more than maybe an amp to maybe 1.2 amps. It would be on the high end, and any more than that, they're gonna just get smoked. So you have to really kind of be careful with those types of things. But that's kind of one way that they do that on the heating thermostats. All right. Now, interestingly enough, in the cooling side of things, the cooling thermostat actually has what they call a bimetal as well, similar to the heating side. And what the bimetal on the heating side is, or on the cooling side, is going to do, it is going to, if you notice how this line is drawn below the contact point. This right here is the contact point, this little device right there, that circle. So this one, when it gets warm in a building, it's going to rise up, and it will eventually make that contact. It'll close that. So that's what typically happens on a, let's call it a rise, or a make on rise is what they're referring to it here. So that's, whereas if you notice on the previous one, you'll notice this line was drawn above that contact point. So that one opened on a rise, heating. This one closes let's say it closes on a rise or it opens on a fall in temp, you could say. So logically, when I see that, that immediately tells me what it's trying to do. The other thing that you'll notice in here, they're also identifying the on-off section here for the cooling. So this is really, are we going to allow it to cool or are we not going to allow it to cool? Now, additionally, this is interesting how they show this image here, but this is good. The thermostat also is taking 24 volts, and the way that the, let's call it the mechanical thermostats, like the old Honeywell T87s and that style, those are the round styles. They had a sub base that used to be that was used, or that's still used. It's called the Q539A sub base, and that sub base would have, I'm gonna get into here, whoops. That sub base will allow power to flow directly to the fan on auto switch. And of course, when you wanted the fan to run with the air conditioning, which is typical, so this is something important to note, is that when there is a cooling demand and this circuit closes, that would send power to the compressor circuit or the cooling circuit, and it would also send power to the auto terminal. So that auto terminal now would allow the fan to have power. Typically that would be going on to a terminal G, or let's call it a G terminal. And then the cooling side, it may be going to a Y setup as possibly. And then this setup here simply just allows you to bypass the thermostat altogether. And if you want to run the fan and you want to run it all the time, you're just going to switch the fan on auto switch to on, and it basically completes the circuit and away you go. And that's typically how that would end up going. So interesting setup on there, and obviously on this on the left side that would be different. So let's take a look at one of the things that's not shown here specifically, but I'm going to bring it to your attention. So in your textbook, there's an image, figure 21. This one that's shown here is figure 20. In figure 21, they call it a cooling compensator. And what I want you, I'm going to draw this cooling compensator in the circuit so you understand this. But what the cooling compensator does, it's like an anticipator, and what it kind of does is it's a fixed resistor. It is not adjustable. And it's a resistor that is in parallel to the thermostat. So the only time that this resistor is energized is when the thermostat does not have a demand, and it's a very small amount of current. They call it a cooling compensator, is what they're doing. The idea of that cooling compensator is to really, I would say it is designed to prevent, let's say, short circuiting, or it's designed to prevent the cycle. It's trying to control the cycle rate to some extent, but in a fixed manner. So so basically when it's off, it's kind of saying, hey, it's getting warm in here, it's getting warm in here. So it's going to allow the cooling system to turn on a little quicker. There's really nothing to troubleshoot in that circuit, and if it were defective, the only way a person would ever know that it was defective is either something would be smoked, or it would be a situation where they're complaining about, the customer would complain that the differential is too large between on and off points, and that would be about it. So again, that's rarely ever that you would ever have to troubleshoot that. So electronic, thermostats today, the digital thermostat, nowadays that's primarily all that we're seeing for the most part. So they are thermostats that are using thermistors, and they're using electronic programmable circuitry that allows changeover. If a person wants auto changeover, it gives you a lot of flexibility into the system. So I can still select my heat, my cool, I can operate my fan like I did on the old mechanicals. However, it's intended to provide more accuracy and allow more flexibility, and maybe even time schedules, and just many different features in addition to that. which would be typical. So when you start getting into and by the way, on the previous one, the old standard thermostat, so a lot of those thermostats, when you wanted to have, let's say, 1 stage, 2 stage, whatever it might have been, you would have had to go into the controller and program the controller for the mode in addition to, like, so whether it's heating or cooling. You'd also have to program your cycle rate. So there isn't, in these, there are not, let's call it anticipators anymore, but what the anticipator was replaced by was something called a cycle rate adjustment. And the cycle rate adjustment allows you to either increase the cycle rate if you want to have a tighter band, or decrease the cycle rate if you want to have a bigger swing. So for example, where I've used this before is if I have a furnace that's maybe oversized and it's cycling too much and it's starting to damage the controls, I would typically go ahead and energize, or I would basically go in and program that circuit to maybe decrease the cycles, but which is going to mean that it's going to actually run longer and you're going to get a bigger differential between on and off. So that's really the big thing. If you have a thermostat that does indeed have a, let's call it an automatic changeover function, which automatic changeover means that if you want, if you set it to auto, and the temperature in the building would fall lower than the set point, it would energize that heating. And if it got too warm, it would turn the cooling on. So commercially, sometimes people will do that. Residentially, it's not typical that most people are going to do auto. Most people are going to just either set the mode, but it really depends on the customer how they want to do that. If you have the ability to, and all the thermostats are going to have this, but they'll have what they call a dead band within the thermostat and on an auto changeover thermostat, and that could be anywhere from 2 to 3 degrees as a general rule. You don't like it to be too close, otherwise you're going to get it switching modes from heating to cooling. So a dead band is important. Commercially, that's commonly done on there. So looking further, let's take a look at some of the more advanced thermostats. So now the beauty of this, you'll notice on the upper right here of the image, you're going to see that there is a Wi-Fi signal on there. And one of the beauties of your Wi-Fi thermostats is now you have the ability to dial it up on your phone or your tablet, and you can go ahead and change set points, and you can do a number of functions and features that are really outstanding. And those types of functions and features allow a lot of everything from troubleshooting, remote like scheduling. It just allows me so many functions and features. It's really incredible how those can be used. Many of the Wi-Fi thermostats, however, do require a common connection. Now, they don't all do that, but many of them require, in the wiring side of things, you're going to need all of your normal wires, but now you're going to need a common to actually operate the thermostat. So that's kind of a typical way to do that. And there are some versions out there that don't require the common, but it's one of those where those are considered as power stealing thermostats, and they tend to use part of the circuitry of let's call it the non-operating systems to use as their common. So they might use the W or the Y or the G circuit to complete the circuit, and that's kind of how they do that. But so a person has to be somewhat careful on some of those things. The other thing that's really nice on a lot of these, like our phones today, is we've got touchscreen. And so nice digital display. It's backlit. It's pretty good. One of the really nice features that these advanced thermostats and electronic thermostats have done for us is it's actually almost eliminated the need for, let's call it anti-short cycle rates. So in other words, we can take where maybe you have in years past, we would have had to put an anti-short cycle timer on a compressor circuit so that we didn't short cycle the compressor. And nowadays, you can put in a 5-minute delay between cycles so that you don't allow your compressor, or if somebody turns the thermostat down and then decides to turn right back up, or vice versa, you're not going to allow a system to actually turn on and turn off and turn on and turn off, and it's a much better application. Good temperature control, a lot of different things. There's so many features. On your textbook on page 18, they talk about quite a few of the advanced features that you get. So, like one of them that I kind of like is if I go into an application and I just want to set the heat up for a little bit. We have thermostats in our lab where we'll turn up the thermostat maybe for 2 degrees, and it'll ask us, well, how long do you want that to go? So, well, I want it to go on I can either do it permanently, or I can do it for an hour or two, or whatever it might be, whatever the limitations that we're setting in there as an override feature. And then the next time it goes through the cycle, it goes right back to where it was originally programmed. So I don't have to worry about, oh, gee, I forgot to turn the thermostat down. So that's really, really nice. Some additional features that are really advantageous on a lot of these thermostats is you have the ability to have things like your battery backup. So in other words, once you program it and the power goes out, you're not going to wipe out the whole thing. Some of them will use different, they might even have a double EEPROM where it holds everything, or they might use a capacitor to provide a power source for doing that. But it's pretty incredible how they do that. But Wi-Fi was really just an incredible, using the internet, it's phenomenal how that works. So very good, very good. But lots of different functions and features. Everything from controlling a heat pump to a standard system, so it's really amazing. So part of, I guess I should back up a step. One of the things that's mentioned and talked about in your textbook also are essentially line voltage thermostats. And a lot of our thermostats, this one, the standard one, this, and all of these, they're generally designed to operate with low voltages. However, in commercial jobs and some residential jobs, we might have a line voltage thermostat that they might control using either, it could be like a pressure sensing bulb, or we call it hydraulic sensing, or you could look at it as, it could be a bimetal sensor. And we might use it to, hey, if as an example, if it gets too hot in this room, we're going to energize an exhaust fan. Or if it gets too warm in an area, we might turn on this fan to exhaust a bunch of the air out of this room so it doesn't get too warm. There's different ways that we'll do that. And there's lots of different ways on there. So a lot of those types of applications are good, they're reliable, they're conventional. In some ways, customers may prefer the old line voltage style over the advanced things for certain safety features in some ways. So also, line voltage thermostats, they were actually subject to a condition that was called what's called thermal offset, and we would kind of refer to that as droop, D-R-O-O-P. And what it would do is the droop would cause that thermostat control point to shift away from the selected set point. So whatever you had for that set point, it would kind of drift away from that. And it would create a little bit of a problem with changes in the thermostat and how it's sensing. So, and this is typical of what would be going on with these line voltage thermostats. And the whole reason for that was primarily due to the current flow that was going through the contacts. So there was a certain amount of heat that would go on as it would carry the load on there. You typically, you don't normally see that happen with the low voltage thermostats, But you can almost equate it similar to an anticipator to some extent. So interesting. So let's get into the next part of this. 2.2 talks about thermistors, and specifically what I want to focus on in this thermistor. So most of our units nowadays, they have a thermistor. Electronic thermostats, they all have thermistors in there. So what I want to do is, and this is an important part of this, thermistors have a curve. And what they do is they give us a certain rate, and sometimes I'll see this as in a table form. Sometimes I might see it in a graph like you're seeing here. And what they identify is the temperature of that versus the resistance of this particular device in thousands of ohms. So they're calling it K ohms. So that's basically your kilo ohms. Now, so for example, and this chart isn't super detailed, but for example, they're showing me at roughly about 77, 78 degrees, give or take, right up in this area. That would be approximately about 10,000 ohms is the way they're identifying it. Now, there are two different types that we might be seeing. One of those might be what we call NTC, and the other one is called PTC. Now, one of them is the N stands for negative, and the P would be positive. Now, what do you do with this? What do they mean? So it refers to the coefficient of the performance of this, whether does the resistance go up with temperature or does it go down with temp? So for example, let me explain. So in this picture here, as the temperature in this case is getting warmer and warmer and warmer. Okay, so let's say we start at 20. At 20 degrees, we might have had 45,000 ohms. When we started getting warmer, so as the temperature was increasing, okay, or getting warmer, as the temperature increased, what happened to the resistance? So then the ohms, in this case, the resistance was doing what? So the resistance, as you could see, is dropping down. So in this particular case, we would refer to that as a negative temperature coefficient. So this one here, as essentially that's what we would refer to as the NTC. Now PTC would be the opposite. So we could say it as the temperature, in this case, rises, the resistance would also go up as well, or the ohms would also go up, and that would be considered as your PTC. So some of our safety devices do that. Almost all of our temperature devices that we use, sensing devices, almost all of them use NTCs, but you never know. It can be completely the opposite. So bottom line is, what do I do with that? And for example, what I have to know about this to some extent is to recognize that thermistors do degrade over time. I need to know that the resistance will change. So if I'm going to check out, if I have the ability to check a thermistor, I'm going to have to check resistance of the circuit, of the sensor. That's typically, most of those thermistors are operating under a very low voltage, but we use a lot of them. So the manufacturers can design a circuit board to look at the resistance change. And what they're really doing is sending a certain voltage, a small voltage, through the thermistors and looking for what the current draw or the voltage drop coming back to it is. So in the circuit, and then that's how they use it. That's how they define or determine whether it's 72 degrees or 80 degrees or 90 degrees. So they have the ability to deal with that. So it's very interesting on how they set that up. Obviously, the one thing you have to recognize with all of these things is they should read something. They should not read zero. They shouldn't be infinite. They should have some measurable resistance if you're checking those out. The other thing that would be probably important to recognize is that the resistance curves are different for different types of sensors. So you have to really get this from the manufacturer of the sensor or the thermostat or of the equipment to allow you to do that. So that's fairly typical. I want to show another one here, and this particular system is shown as a thermistor that would be used in an expansion valve system. And one of the things that they're doing in here is they'll use the thermistor to, the thermistor is going to measure the temperature of the refrigerant coming out of an evaporator. And that's what they're showing right in the circled, the red circled area. Now this particular system is going to look and say, all right, there's going to be a certain voltage going through that thermistor. And again, the manufacturer has to figure all that out. And they're going to have that go through that circuit, and then there's going to be a certain voltage drop due to the resistance of that little thermistor, and then it's going to control, let's call it some sort of a thermal expansion valve or an electronic expansion valve. Now that obviously you'd have to know specifically, the manufacturer would have to design the system, the control circuit, to look for certain voltages that would be normal, normally what I would expect. So it's a specific control system that would have to be compatible. You just can't go and just grab any old thermistor and say, I'm going to run 24 volts through it and make it work. That typically doesn't happen on those systems. Okay. I actually want to back up a step here. So I talked a little bit about PTC, and one of the things that we look at with our motor circuits is there is such a thing. If you look at figure 28 out of your textbook, there's such a thing as a PTC thermistor, and we call it a start assist device. And that works the opposite of this particular graph. In fact, let's say the sensor is very cold, the resistance is cold, and that allows me to get some, let's say the temperature drops, the resistance would indeed drop as well, and that would allow for more current to flow to the start winding. So in that image, that's really what they're referring to is they would put that in parallel with a run capacitor for starting a compressor. So that's kind of one of their little, what they call a hard start kit, but it's probably better defined as PTC start assist is really what it is. All right. So let's move on to this next one here. And so for example, this one is showing me multiple thermistors or sensors that are embedded into the motor. And they are sensors that have leads that would maybe go to a compressor or some controller. And the sensors would have a certain resistance based on their temperature. Just like that previous picture, it would show that. They would have to give you what the resistance is per the temperature. And again, it should be a measurable, we should have indeed a measurable sensor, measurable resistance, and it should not be zero, and it shouldn't be zero, and it shouldn't be infinite. It has to be some sort of a mechanism that would be in there. But we do all kinds of different ways that we'll set these things up, but that's typical how it is. So usually, in most cases, I would say a lot of my thermistors, if they're broken and open, then they're going to be an open. If they are, let's say they're just out of calibration or they're drifting, it's probably time to change the sensor and as opposed to calibrating it. But that is something that some of the electronic thermostats will do, is they will actually go back and you can come into a control like this and you can put in, let's call it a calibration offset in some cases. So if you know that the sensor, hey, the thermostat that I have, it shows me that we should be 74 degrees in the room. That's the temperature, but the thermostat on the wall is telling me that it's 72. I can put it in an offset, and calibrate it. All right, so installation. Let's talk about some of that. So there's some obvious things. A lot of the, at this point in your career, for all the level 3 guys, you recognize that you would expect, you've installed thermostats before, and some of the things that you have to be aware of, what things you should not have done. And as an installer, and maybe nor as a service tech, now you have to be aware of all those things that you should or should not have done. So I'll give you an example here. So we talk about thermostats not being installed. You know, you wouldn't want to install them where you're going to get a draft, or you're not going to getting any, really not a representation of what's in the room. So you don't put it right by a door. That would be an outside door. You don't put them on outside walls. So you don't want to put them on, if you're going to have air from the diffusers blowing directly on it, you would not want that, you know, whether it's heating or cooling. You don't want them in the line of sight. If you don't want to put them near appliances. So I talked about earlier about don't put them, you know, next to the copier or next to the refrigerator. You got to be careful because you do pick up some heat from those devices, and that can really create some discomfort. The worst part is it could be temporary. So in other words, I've had guys in the field, they install the thermostat and the customer decides they're going to put a coffee maker right underneath the thermostat, and then they wonder why they're so cold. The coffee maker gives so much heat up, and before you know it, it's wanting to get cooling in there. So that's one. So other things, obviously, you try not to put them near concealed ducts or anything like that, chimneys, things like that. You can pick up heat or cool from that way. And then obviously, you want to make sure, typically you're always looking for, interior walls. You don't want them on outside walls if you can help it. You don't want them on walls that have a lot of vibration. Now, this was a really big thing when we had the mechanical thermostats. If a person were to close a door or slam a door and a Mercury thermostat was by it, the Mercury would kind of jiggle and you could have your system operating on and off really fast, and that you don't want that. So that's kind of one thing. So that makes sense. Vibration creates problem, but the electronics, you still wouldn't do that, but the electronic thermostats really stabilize things a little bit on there. So additionally, we can take a look at this one. So we're talking about installation on 231. And one of the things sometimes that we have to do, and this is especially important if you have air that can make its way from like maybe inside the cavity of the wall. And you can, in some cases you might have to put a little bit of, let's call it duct sealing or wire duct sealing, and it's like a putty or thumb gum as an example, and you can seal around the wire. What we used to do was we'd stick insulation around the wires, and so that there wasn't any drafts that would be getting into it. So that's one thing, and you'll make all the connections. There are obviously all of these thermostats that are electronic nowadays. They don't generally have, will they work without being level? Yes. That's not really a major requirement anymore like it used to be, but most thermostats have a sub base so that when you do mount it on there, there's a couple of pins that allow you to identify, putting a level on it, you can say, hey, this is level or this isn't level. And obviously quality installation to look good, you'd want it to be level. So that's one of those typical things. So they're showing you a couple of the pins that are identified on there. Some of the things that you'll notice on the thermostats and the connections, you'll notice certain designations and certain wire things. So for example, when we look at this thermostat, you might notice like this one, this is not necessarily installed the best, but you'll notice how there's a fair amount of wire sticking out of where you put the wire into and screw it down. That's not really very good, but you will notice that in the other areas, the W that's shown right here and the Y, notice how they're much shorter. That's a little more appropriate, and simply because you do not want to have any of those wires breaking off and shorting out or anything like that. So that's kind of one of those that would be important on here. So the S1, S2, that's probably like for an additional sensor that maybe you want remote sensors. So anyways. So let's talk about some of the codes and some of how you're going to wire them and what are the terminal designations. So typically what I normally have guys do as we do this in the lab is you take a thermostat and you kind of look through the install and you try to figure out what am I looking at. And there are certain functions that I want to bring you about. And one of the things that you have to figure out is this an electronic thermostat, or is this that's controlling a conventional system? Is this a thermostat that's controlling a heat pump system? Is it dual fuel? I have to know a lot of those. What am I going to do with it, and what am I controlling? So on the left side of this chart, and on page 23 out of your textbook, they give you a chart that talks about some of the wiring terminals, and specifically, and they might give you some suggested colors. Common, sometimes people use black, sometimes people use blue, sometimes people use brown. It depends on what you have for available colors as a general rule. But I would say that there isn't any universal color for that. The R terminal designation is typically the red, and normally we would do that as considered as the power. Now that could be power for heating, it could be power for cooling. They could be separate. So a G terminal typically is your green. That typically is what we would have put to the fan terminal, and that's what's controlling your fan. Now the Y terminal is normally either going to be yellow, or it could even be the blue wire. It depends how many stages that we have. But that typically refers to compressor operation. So now your book will refer to it as a cooling control function. I would say that's true of a conventional system, but if it's a heat pump, it will just refer to as cooling, or as compressor operation. So it would be very good to read through that section in there. The one area that we're missing in here would be your W connection. Now this particular one here is showing that. So you'll notice there's a thermostat on the left side. We have terminal R. That's pulling 24 volts from the unit. So that could be a furnace or an air conditioner. You've got your W connection at the thermostat base going to the W on the heating, the Y to the Y, and your G to your G. So it's pretty obvious that you're connecting point to point in this system. So on some of the thermostats, they may have multiple designations, and you have to, depending on how you program it, will determine how it works and which terminals to wire to. So you have to look at that a little bit to see on there. But it's like I said, that's typically on the sub base of the board and whatnot. All right, cycle rate. So earlier I had chatted a little bit about something called an anticipator. Well, we try to get away from the anticipators and go away from that, and for good reason. The anticipator is kind of, let's call it old technology. The cycle rate gives us so much more flexibility of an install. And obviously every thermostat is going to have their own set of instructions to determine whether it's, what your cycle rate would be. I think the bottom line is, if you're adjusting the cycle rate on an application, I think what we're trying to do is we're trying to figure out what would be the appropriate amount of cycling of this appliance in an hour. And so they usually are identifying it as cycles per hour. So if it's a furnace, maybe you wouldn't want it to turn on and off more than maybe 4 times, anywhere from 3 to 5 times an hour. And if it's an air conditioning unit, maybe you don't want it to be more than 3 times an hour. So I usually look at it this way. I said, whatever the cycle rate is, take that and divide that into 60. So if it were 3 cycles, that would mean it would generally turn on and off once every 20 minutes. 60 divided by the 3, and that's usually how I look at it. I've had appliances that were very, very oversized in applications, and the fix or the best remedy that I can do without replacing the unit was to put an electronic thermostat and adjust the cycle rate to try to help control that. So Mercury thermostats. So as I had mentioned earlier, the Mercury thermostats are very hazardous. They're very dangerous. They're in the wrong hands. Create some serious health effects for people. So the Mercury thermostats typically when you pull them out of jobs, you bring them back to the shop or you bring them to the wholesaler and you allow, usually they'll have a recycling bin and they'll take them off your hands. But yeah, you do want to be pretty careful on those things. There's a lot of rules behind that. So, all right. So let's take a look at some of the troubleshooting side of things a little bit. So first of all, thermostat troubleshooting. So another, first thing, you look at where it's located. Is it a good location? Is that a problem? Is that creating some of our issues? Are the switches set? Is it programmed correctly? That isn't as simple sometimes to go through the programming, because you may have to find the book to be able to do that on some of these thermostats, because there might be a code or a certain sequence of buttons to be able to get into it. If it's a thermostat that's got function switches, do you really have it set to heat? Or if the customer's saying, hey, I don't understand why my fan runs all the time. And you go to the thermostat and it'll say fan on. Well, not everybody is well versed as all of us in that. Mercury thermostats. Those are thermostats that are extremely level sensitive. So I'm going to go back to this. So in other words, the little mercury that's in here, that is going to swing one way or it's going to move the other way. And what it does is depending on the bimetal that they're showing here, that wire wound bimetal, that will tilt one way or tilt the other way. And what it's doing is it's actually making a set of contacts. So like this pin, these little wire pins in here, that's what it's doing. So you'll notice it there. Very, very reliable, but they're kind of a hazard. So that's one of the reasons why they had to get rid of those. But it's very level sensitive. I think of some of the applications where the maintenance guy on the job decided to move the thermostat, take it off the wall, and before you know it, he puts it back on, thinking nothing about that has to be level to function correctly. So you can see jobs very easily out of adjustment. They might control the job 5, 10, 15 degrees variation from the set point, just simply because it's so far out of level. So, all right. Additionally, some of the things that we look at when thermostats aren't working correctly is, look at the voltages. What are the voltages? Are they appropriate? Is it what we should have? Most of the thermostats will be controlling 24-volt circuits. Look at the jumper wires. Are there dip switches? There's a lot of different applications where we would have done this. So find out if that actually works in the way we want to do that. So sometimes when we have a thermostat that doesn't work or equipment that's not working, I think it makes a lot of sense sometimes to, let's go with jumper wires and let's try to figure out whether it's a thermostat or whether it's the wiring or the equipment. So if I were to go to the thermostat and I put jumpers on the terminals where we wired it to, I would enable certain modes, and I should see the result of that or the changes of that. Those are the things you have to do. And if all of a sudden you do that and it still doesn't work, now you better be looking more at wiring and equipment. So maybe you go to the equipment and you put in, hey, let's go ahead and try to jumper those terminals there. And so you can identify what's wrong or what's right. So here's kind of a couple of things. So if I wanted to test indoor fan function as an example here. Now, one of the things that I could be doing is and typically the way I will usually test circuits, thermostat circuits, is I like to go to a common. And so if you do that, then you're actually looking for voltage as opposed to not looking for voltage. So in this circuit, if the fan is intended to be running, you're expecting 24 volts right here. So between the common and the fan operation, the G, the meter is picking up 24 volts. That's what I would want. Now, if I were to go between R, the R terminal, and G, I would be looking for 0, simply because the R terminal is actually sending voltage to G if it's working correctly. Now, here's the problem with that. If I don't have voltage at R, it's also going to read 0. So a person would have to, if you're going to do that test, you probably want to make sure and check your voltage between the red or the 24 volt hot R terminal and the common to see, do I really have voltage here? Then, if you go between the red and the G, if it is indeed calling, you would expect 0 on that meter. If you read 24 volts on that meter when you go between R and G, that would tell you that that circuit is actually open, and it's because there's a potential difference on there. So those are the things you have to look at. Here's a circuit looking at the Y and the W circuit, and again, this is a much better way to do it, where you're looking for positive voltage. So I want to know, am I calling for cooling? So between Y and common, yes, I got 24 volts, perfect. I want to see if the heating is operating. Give it a heating call. Do I have 24 volts? Yes, I know it's working. That is by far the better way to do that. All right. Additionally, some of the units will give you, they'll have troubleshooting guides that might get into some of the, hey, this isn't happening or this isn't working, what should I do? And they might ask you certain questions and flow charts that might be on there. In programmable thermostats, some of those responses, how you program it, will affect what actually works in there. So you really have to learn the book and figure that out. So it's very important to be able to do that. On page 39 or page 29, there is a figure 39 that goes through several, it's basically symptoms, possible causes, and corrective actions that allows you to do that. So, all right. Let's go through a couple of questions and we'll finish this section up. So, common deadband that prevents heating and cooling set points from being too close together would likely be approximately about 3 degrees. And in this case, that was what we had called like a deadband. So that's it. An open thermistor would be indicated by having an ohm meter reading of, so if it's open, there's no current, I would have to say that would be more likely an infinite amount of resistance. Third question is, before handling an electronic programmable thermostat, always, so read the instructions, ground the thermostat, install the batteries, ground yourself. It probably is wise, due to the static electricity that a person has, to likely want to ground yourself to something, especially if you're walking across carpet. That's true with anything electronic, is you want to somehow ground yourself. So if you go to the thermostat and you touch that thermostat and it makes a spark at your fingertip, that's probably not good for it. So grounding yourself would be one. Fourth question, it says to ensure correct system and thermostat operation, the control circuit voltage should be not lower than. Okay. Now, this one could be, again, the key thing is control circuit voltage. And now the question is what would you like to see and what is really needed. So if there is not a load on it, I would expect to have at least 24 volts. If there is a load on that, it could be a little bit lower, but you rarely see that happen. So in this case, not lower than, if you take the 10% off of the 24 volts, that gives me about 21 volts AC. Again, thermostats will work at 24 volts. If you start getting less than, taking away 10% off 24 volts, you're easily going to be down in that 21, 22 volts. That's starting to get a little iffy on there. So, all right, that concludes section 2, and section 3 will be next, and that'll be another additional video.